One of our last sections on our aromatic rings would be reduction. I know a benzene ring seems super unreactive, and we've already addressed how it could act as a nucleophile in the EAS reaction. We didn't really address kind of the reduction of them, as in a loss of the pi bond. And that seems very, very unlikely because you would then remove aromaticity. Right? But it can be done. And because it can be done, even though it seems like you can't, it also gets a name associated with it. So we'll hear it as a named reaction. So benzene can be reduced similar to our alkynes. In the alkynes, we use sodium metal, and it goes through what is known as a radical anion mechanism. And that's because the reactivity of sodium is that it has that extra pair of electron, or not extra pair, it has that one extra electron, and it's really trying to offload it due to its low electronegativity. And so we end up seeing a radical mechanism that goes through and produces our radical, and then we would also get that bond to sodium because we now have a pair of electrons, but because that is an ionic bond, you could rather think of that as a lone pair of electrons on that carbon with the sodium as a cation. It doesn't want that lone pair, and so it very quickly tries to find something positive, and that something positive happens to be the solvent ammonia. And ammonia does a pretty darn good job of solubilizing electrons in active species like this, and so we end up doing a reduction of it. That free radical on the other side goes through the same process with another sodium to form another radical, and then we neutralize out. And the trick with that one, or with the alkyne, is that we end up getting that trans alkyne, and that's because the radical anion, it wants to minimize energy as much as possible, so those large groups get as far away from each other as possible, which is what I was trying to gesture, but didn't have the words to back it up. Right? It does a similar process with our benzene. So if you wanted the fancy mechanism, there's the fancy mechanism. Of course, the mouse is hiding. Okay, benzene can go through and do something similar. Okay, and this is what's known as a Birch reduction. So we've got the mechanism shown above, but I'm about to delete it and kind of walk through it. Whoops, that was not what I thought it was. And walk through this process with our benzene. Same general idea. We go through with that first step to form that radical anion. And remember that it is, or it was, aromatic, and so it wants to kind of return to being aromatic. And the problem with that is that if it went through and did that, we would have to kind of offload those electrons. So one of the things that tends to happen here is that we're trying to destabilize the potential for aromaticity as quickly as possible. And so there's a variety of ways that we could draw a resonance structure, the easiest of which would be to do something like this. And the point of drawing this resonance structure is that we have now actually kind of minimized the ability to restore aromaticity. By separating those double bonds away from each other, we've kind of lost that conjugation, and now that anion can come out, anion can come out, pull off the hydrogen from our NH3, and thereby continue our reaction. Okay, and so similar process as the alkyne reaction. The thing that's going to make this one a little bit more different or interesting is that when we're looking at benzenes, particularly benzenes out of EAS, we aren't looking at just benzene. We're concerned about a secondary group on it. If I go through and put a CH3 on there, not all of those double bonds are identical, which then means which double bond or which pi position is most active or most likely to react. That process is very similar to our EAS, and that what we're looking at is how we stabilize those intermediates. Okay, remember, the primary kind of mechanism behind this, as I keep oscillating back and forth between drawing and not, was a radical anion, our intermediate has a negative charge. If we had, say, a methyl group on there, do I want the anion to be forming at that position? Okay, should I have an anion ever form there? Okay, well, hopefully you would say no. And the reason being is that we would then have, so I keep trying to draw and using the eraser. If we had the anion there, that means our double bonds are located over here. There's our radical CH3. Okay? We would be having a tertiary anion, and that's the least stable anion. So if I had something like that methyl group, I don't want the anion forming there, which means the double bond should stay there. And that if I drew out my structure, CH3, I want the double bond here. Remember, we wanted the double bonds to not be conjugated. The other double bond will get placed on the other side. Okay, so cool. That kind of helps us. If we're looking at that atom, we're considering the stability of the anion in that mechanism. So what would happen if, say, we switched this up, and instead of it being a CH3, let's go ahead and put on a nitro. Well, what was the difference between the nitro and the CH3? Hopefully we're remembering that the nitro is electron withdrawing. Right? It's putting a positive charge next to the ring, which means it would absolutely be a good idea to put a negative charge immediately there, because if I had a negative charge there, I could then stabilize both the negative and the nitrogen through resonance. And so now my double bonds will appear to the sides of the substituent as opposed to directly connected to it. So what we're doing is, again, looking at that atom X, that atom immediately connected to the ring, and we're deciding, is it electron donating or withdrawing? If it's electron donating, I want to put the double bonds immediately next to it. Okay? If it's electron withdrawing, I want the double bonds as far away as possible. Okay? And for those of you saying, well, it seems weird, aren't we referencing the electrons? Yeah, we are. I'm also trying to give you, in the short amount of time that we have left in this semester, an easy way to memorize this reaction so that you don't have to boil down all the individual mechanistic details behind it. Okay? It's about trying to zero in on where those double bonds are located and trying to help you out in that respect. Okay? There's the big long version of the mechanism, so we could look at it. Or I already started to draw it, but here you've got it drawn out for you. And the big kind of bottom line picture comes down to what we're trying to decide with these two kind of systems, looking at atom X where it's donating or atom X where it's withdrawing. And what we just addressed, everything's drawn up, I think the way I want it to be drawn. What we just said is if we had a donating group, we want the double bond next to it. And if we had a withdrawing group, we want the double bonds as far away as possible. Okay? Why? Well, go back to our mechanism. If we had that R group up here on the top, okay, electron donating, we're putting the negative charge off to the side. Okay? If we go through and do an electron withdrawing group, so we'll draw that underneath for our mechanism, we'll call it EWG, where do I want the negative to be? Well, I want the negative to be at that position. And if the negative is there, the double bonds must be on either side. Okay? So it's really kind of trying to recognize the utility and the power, drawing group, double bond, radical. And what we end up doing is kind of a pseudo rotation, at least it appears to be a rotation. Okay? And this is what's helping to stabilize this. We could go through and continue. We'd put the negative charge on. When it went through and did another system, and in fact, arguably, if we look at this structure, we would probably do something, oop, never mind, ignore that. I was going to try and do resonance, and that was a bad idea. Okay, so that very first position becomes our clutch. That formation of the anion, where do I want that anion located? If I have an electron withdrawing group, I want the anion as close to the electron withdrawing group as possible. If I have an electron donating group, I want it as far away as possible. Okay? This is negative negative or negative positive. It's aligning those charges, which is the thing that I've been trying to get you to do the entire semester because it predicts so much. And I believe we've got the answer drawn in so we can go through and see it. So note when it's electron withdrawing, we don't see the reduction happen at that position. We have the double bond still there. Okay? And if it is, or sorry, electron donating, we don't see the reduction. If we see it an electron withdrawing, that's the position that gets reduced. Okay? And that's all dependent back on the formation of that first anion species, and I want that anion to be stabilized as much as possible. If the electron donating group is at that position, it destabilizes that intermediate, which means it reverts back to the starting material. If the electron withdrawing group is at that position, it is stabilized, allowing it to continue forwards. Okay? So Birch reduction was the name. I think that popped up. I didn't actually emphasize it, but it's known as the Birch reduction. Again, your donating versus withdrawing groups are going to play a pretty big role in predicting where those substitutions happen, and you'll see it pop up. Okay? You'll see both answers show up as a possible choice. So make sure you're aware of that when you're going through and looking at it. And with that, we're also done with this one. It was a relatively quick video, just looking at that reduction and trying to evaluate some of those considerations. Okay, thanks.